Hello again to the video series. If you've been following along kind of in sequence, the previous video was z-score for an individual observation, and really again we were looking at one observation. Now we're going to be looking at a group of observations to compare to the population. So again, if you go back to our housefly example, in the previous video we had the one fly. Now what we were comparing to all the rest of the flies in the house. Now we want to look at a small sample of flies in a specific situation and compare to the larger group of flies. But the issue that this brings up is, when is something a sample and when is something a population? And this is also going to become important because it's going to affect the notations that you see in the video series and in your textbooks. And it's very important to know conceptually what you're looking at so that you can be on the right page in your brain when you're looking at the statistics. So we're still dealing conceptually with exactly the same thing between a population and a sample in terms of what we're computing. We just have to use different notations. So we've already talked about calculating an average or a mean. If we're doing this for a population, we're going to be using the symbol mu to indicate that that's the average for a population. But even if we have a sample, we will still want to calculate a average or a mean for that sample. It's just that when we're dealing with a sample, we'll be using a slightly different notation. In that case, the notation that I use, that I prefer, is called x bar. It's literally the variable x, but with a line above it, and so we call it x bar. Different textbooks will use different notation for some of these, so you just need to check your textbook and find out what notations that they are using. Many textbooks actually use capital M for a sample mean, simply because I think typographically that's easier to do in the print industry than X bar. In fact, as you look at the X bar on these PowerPoints, the bar is actually kind of cutting the top of the X. Really, it should be sitting above it. So that typography can be a little bit difficult to create at times. So again, they're both averages, they're both means. We're just in one instance referring to a population. In another instance, we're referring to a sample. Prior to this, of course, we did also calculate the standard deviation. So again, as we look at this, we have lowercase sigma sub x. That indicates the standard deviation for a population. If you've been watching the video series, I had what I call a mantra that I make my students memorize. I wonder if you can remember what that was. If not, I'm going to reiterate it very quickly. Again, I encourage you to memorize it. The mantra is, standard deviation is conceptually the average distance of one observation, unobservation from the mean. We will also be able to compute a standard deviation for a sample, but as you note, the sample standard deviation will be indicated by capital S sub x. Again, different textbooks may use different notation for this, so just figure out which one yours is using so that you have that in your head, so that if I use S sub x, you can mentally think, okay, my textbook is using this, but the concept is exactly the same. What we have not yet covered, but we will be covering in this video, is the standard error of the mean. So it is still lowercase sub x as before, but in this case it's going to be lowercase sub x bar. So again, that's the standard error of the mean. Instead of just lowercase sub x, it's lowercase sigma sub x for the standard deviation, lowercase sigma sub x bar for the standard error of the mean. As we look at the sample, it's effectively the same thing, but we're using capital S sub x bar to indicate that. The other one I try to be very meticulous about. For a population, when referring to n, its number of observations is going to be capital N, whereas for samples, I prefer to use small n. In most situations, that's going to work for you, but as we get to the more advanced statistics, n is going to become a little bit more ambiguous than just population and samples, so you really just have to look at what computation that you're dealing with at a given moment in order to make sure that you're getting the right n for that particular computation. So, sample versus a population. In simplest terms, and there is some debate and differences of opinion over this, if you will, a population is all possible observations of your intended measure. In the case of our houseflies, it would be the wing lengths for every housefly. Usually, that definition makes it a practical impossibility in the broad sense. Populations are still the basis of many computations because there are a few instances where it does arguably make sense to indicate that the measure that I'm dealing with represents a population. So what are some of those special cases? Well, the one that we've been dealing with in the previous videos. When you restrict the observations to a special case. In the example that we've been talking about, we've been dealing with just the houseflies in my house or our hypothetical individual's house. And not only are we restricting the observations to the houseflies in that individual's house or my house, we are measuring all of the houseflies. So it does fit that definition of a population. The other case is when a sample is quote-unquote sufficiently large. It is sometimes considered a population. Why? Because when we have a sample that is sufficiently large, then the difference between a very large sample and an actual population arguably is statistically negligible and really isn't going to have an impact on the outcome of your computations. So again, this is one of those special case situations where there is some disagreement between individuals at times in whether you can call it a population or not, but if you have a large enough sample, often it's close enough. The other special case, which we're going to be dealing with soon in the next video, is when random odds actually dictates what that population would look like. So for example, if I'm flipping a coin, if I do that over theoretically infinite number of trials, if it's a balanced coin, I will have a 50-50 distribution. So statistics, or basically probability, dictates that that population is going to have a distinct shape to it, and so I don't have to measure every coin flip possible because I already know what that outcome will look like. Similarly, if I have a 6-sided dice, then over infinitely large number of rolls, I know that each individual value will have a probability of coming up of 0.167. So I don't actually have to do every observation because I know what those observations will be. Probability tells me what they will be. So these are a few instances when something can be considered a population. So as of right now, we only have one observation from the previous video that we talked about, and that observation, the analysis that we did in the previous video, did lend support that that fly was abnormally large. The wings on that housefly were abnormally large, and so we want to now test if that's actually a causal relationship between the environment in that terrarium and the fact that the fly in that terrarium was abnormally large. So, since we're only concerned with the flies in our house, in the researcher's house, and we've measured them all in that house, then we can consider that a population and still move forward with the standard unit normal distribution, or the Z distribution. We also, in order to test this, don't want to rely on a happenstance observation, but we want to create more of a true experimental design. So in this case, we still have the original terrarium, which led to the suspicion that perhaps the environment was more conducive to fly growth. So the researcher introduces the larvae of 4 common houseflies into the terrarium and allows them to develop into adulthood before he measures the lengths of their wings. In so doing, because that environment is hypothesized, then if the environment is truly the cause, then all 4 of those flies should be in an environment that allows them or causes them to be larger than the population that is dictated by the rest of the flies in the household. So since this experiment has shifted from an individual observation to a sample for flies, we now have to compute the average of that sample, but statistics changes overall a little bit. We can no longer use the Z-test for an individual, but we're going to have to move to a Z-test for a group, and our conceptual orientation is also going to change a little bit. So let's talk about that. What is the difference between a sample distribution and a sampling distribution? So here's the original sample that we started off the video lectures with. We captured 25 houseflies, and as we measured the wings, they all happened to fall out into a normally shaped distribution. That case is a perfectly viable situation. However, it also could have been that had I captured those 25 houseflies, instead of this nice, pretty normal distribution, it's possible that that distribution could have looked like any of these other distributions. I could have had another fairly normal distribution with a slightly smaller average wing length. I could have had a much broader or more widely spread distribution, or I could have had a skewed distribution as we see on the other side here. So anytime we are dealing with a sample, that shape of that distribution can vary widely, even though in nature it does typically end up in a normal distribution. But I'm no longer dealing with a sample, I'm no longer dealing with an individual observation that I'm going to compare to the population. I now have a sample that I need to compare to a population. And so this changes things overall a little bit, because instead of one fly in any of these distributions, I have a number of observations of one fly. I don't have a distribution of what do I expect any given mean or average, sample average to look like. So for that, I have to create a sampling distribution. So what is a sampling distribution? Instead of plotting individual observations, I am plotting the means, the averages of a variety of different samples. So there are a few very important things to note here. In this green distribution, this is not individual observations, but as you notice with the arrows, I am actually plotting the means of all of my different samples into this sampling distribution. There are a few very important things to note here. Notice on my samples, the variance of my samples often ranges from about 4.1 to about 4.9. Whereas when I get to my sampling distribution, the variance there is only from about 4.47 to about 4.53. So what I've done is on the bottom number line here, I've plotted in a sample, we really expect that range to run from 4.1 all the way up to 4.9 on the other side. When we're dealing with individual observations, the sample can be fairly broadly spread. However, once we plot the means, it ends up being much, much narrower and often has a higher peak. I want to step away from the numbers-based, the conceptual base, or the houseflies, and let's step into a world that's maybe a little bit more familiar. Imagine you walk into a store. In this store, there's about 500 people. You point randomly at one gentleman, and that person's height happens to be 6'7". Is that unexpected? Yes. That's a fairly tall individual, so you might indicate to yourself or think to yourself, wow, they're pretty tall. It's a bit unexpected, but it's not out of the realm of possibility. You've probably seen an individual 6'7" a number of times in your lifetime. So you know that they're tall, but they're not out of the range of complete expectation for tall. In fact, if we look at the curve, the normal distribution for male heights in the United States, it's about 5'10" tall. So that individual is a tall individual. You're surprised, but not absolutely shocked by this. But now consider, same situation, you're in a store again with 500 individuals, you randomly point at 10 individuals, and you calculate the average height of that 10 individuals. Now imagine for those 10 individuals, you got the same 6'7", but now instead of the height of one person, you are talking about the average height of 10 individuals being 6'7". Now, if we think about any given sample that we have, what does that mean? If my middle point is 6'7", then on average, we would expect half of those observations to be shorter than 6'7". And since we've already established that 6'7" is an abnormally tall individual, then not only would we expect half of the observations to be less than 6'7", we would expect them to be substantially less than 6'7". We would expect to see some people 5'10" and even shorter than 5'10". So in order to have 5 of these individuals be in the 5'10", 6 foot, maybe a little bit shorter than 5'10", in order to get an average of 6'7", that means the other 5 individuals need to be 6'7" and even taller than 6'7", substantially enough that it brings everybody's overall height when you calculate that normal distribution to up to 6'7". So one individual, 6'7", surprising but not shocking. Randomly pointing at 10 individuals and having their average be 6'7", that would be very surprising and absolutely unexpected. If you pointed down one aisle and got a group of 10 individuals 6'7", maybe by chance you just happen to get a basketball team in that particular aisle. But if you're doing it randomly around the store, that should not happen. It just is really not expected by chance. So that's why when we look at the fact that the range of scores for a sample is much, much larger than the range of scores for a distribution, if we think about it, 6'7" would fall somewhere down here, which for a distribution of individual observations, not so bad. But compared to a sampling distribution, a distribution of averages, that's extremely unexpected. So that sampling distribution is normally much, much narrower because anytime I have a sample, I have some on one side, some on the other side. When I calculate the average, it's going to pull it in to the center. So really what I'm plotting is multiple center points instead of the overall range of the population. So again, a distribution of some statistic, in this case that statistic is sample means, is known as a sampling distribution. A sampling distribution could also be a distribution of medians. It could be a distribution of modes. It could be a distribution of standard deviations. A sampling distribution is simply a distribution of some statistic. Most commonly, especially in this video series, it is a distribution of sample means. So we have moved on from a distribution of observations to a distribution of sample means. So when I was computing the z-score formula in the last video, we were looking at one observation. So if you remember the numerator for that formula, we had x minus mu. I have that actual observation of x, and I want to know the distance of that observation from mu. What's the distance of one observation from the mean? The denominator was the standard deviation. Statistically speaking, what's the expected difference of an observation from the mean? So I have a ratio. I have the actual difference on the numerator because I actually observed that housefly and subtracted the difference. And then on the denominator, I have the expected statistically by chance. I'm creating a ratio. Most statistics are just a ratio of observed over expected, sometimes known as estimated. But if I'm no longer dealing with an individual observation and I'm dealing with an x bar, a sample, I'm now looking at the actual distance of a sample from the population mean. So the denominator can't be a distribution of observations. It needs to be a distribution of means. So that's effectively what this is saying here in the orange box, is we have to shift from a distribution of observations to a distribution of means. So again, briefly reviewing before, when we were dealing with just observations, we measured all of the houseflies in the house, we calculated the mu, the mean for that population, and we had 4.3 was the measurement of the wings of one fly. 4.7 was the measurement of the wings for another fly. When we calculated the standard deviation, we were doing that for individual observations. Again, standard deviation is conceptually the average distance, the expected difference of an observation from the mean. We literally looked at that because when we calculated the sum of squares in order to calculate the standard deviation, we literally took every individual observation, subtracted the mean, and then of course we squared it to get rid of the negative sign, and so we compensated for that by taking the square root later. We're stepping back from that. That's review. I'm reminding you of what you did. We now have to move forward, and we're not using a distribution of observations. We are now using that sampling distribution, which is a distribution of sample means. So, just as over here, we calculated that average distance. What's that expected difference between these two values? We could, over here, theoretically calculate roughly the same thing. We could look at the difference of each individual mean and subtract it from the mean of the means, and then calculate that average distance of a mean from the mean of the means. Fortunately, it's actually much easier to do that. The formula ends up being much simpler, and there's two things that are kind of important here. The formula for the standard error, as you see here, basically just takes use of the standard deviation that we learned how to compute before and divide by the square root of n. That gets us the value that we need, which is, again, conceptually, this is your second mantra, standard deviation, conceptually the average distance of an observation from the mean. Standard error is conceptually the average distance of a mean from the mean of the means. So we've now moved from a sample to a sampling distribution. That's the first important thing, is that mantra and what's actually going on in a sampling distribution. The second thing is mean of the means, and you need to have this locked in your head, is ultimately effectively the same thing as mu. So that's where we would be moving from here. Before, z-score determined if our z-score for an individual, our z-test for an individual, determined if an individual score was unexpected, but a z-score for a group is now needed since we're using a sample and we're looking at the average of that group of scores. So to review again, this is how we computed the z-score for an individual, but we're now moving from one score to the sampling distribution. What I want you to note as I bring up this other slide is notice that this formula here, x minus mu divided by standard deviation, it is very much the same as x bar minus mu divided by standard error. So my goal as I move forward in these videos is to indicate to you that if you get and understand this statistic, the next statistic is basically the same thing. The next statistic will be basically the same thing. The next statistic, and so on and so on and so on. So don't learn one thing for a test or a homework and then flush it out of your brain. Because this course builds on previous information, if you make sure you lock this down good, then the next one is going to be easy. So to compute this statistic, I had to have the individual observation. That's easy. I don't have to compute anything for that. I had to have the population mu. That's not too bad. That's just computing an average. Standard deviation, that was a little bit challenging, but not too bad. If you learned how to do a sum of squares, then the rest of that formula is very easy. So as long as you understand how to do this, we're going to do exactly the same thing. Here we have a sample mean. That's fine. That's my 4 houseflies. I just have to calculate an average. I have to compare that to the population mu, which is just the average for a larger group of individuals, or in this case, houseflies. Now I need the standard error, but the standard error is simply taking the standard deviation dividing by the square root of n. How do we get the standard deviation? Well, if it's not provided for you, you learned that on the previous slides. It's just the sum of squares divided by capital N. So if you've learned this, you're ready for this. You want to basically blow up all these formulas to create your toolbox. What do I mean by this? I know I need x bar, so I'm going to put that as a line in my toolbox. X bar equals what? I know I need mu, so I put that as a line in my toolbox. Earlier videos, we already computed mu to be 4.5. I need standard error. I don't have standard error, so how do I get to standard error? What's the formula for standard error? The formula for standard error right here is standard deviation. Okay. I've already put standard error in my toolbox because I know I'm going to need it, but to get to standard error, I need standard deviation. Put that in my toolbox. Turns out I had already computed standard deviation in earlier videos of 0.2, so now I can fill that in my toolbox. So do I need to go to standard deviation equals sum of squares divided by capital N? Technically, in this case, I wouldn't need to, because to get to standard error, all I need is standard deviation and little n. We're going to have those in a minute, but if you had to keep exploding your formulas, you would now have sum of squares, put that in my toolbox. In this case, it happens to be 1.0, and capital N, the population size of the houseflies in our house was 25, so I can put that in. So what you're doing is deconstructing the formulas into their individual component parts, putting those component parts into your toolbox. Then once you have them in the toolbox, you're just going to start reconstructing the formulas until you get to your final value of the z-score. So you really should be able to fill in the standard error at this point because you have everything you need. You might take a moment to do that, but for right now we're going to move forward. So we again have to break this into actual statistical hypotheses, because now instead of the 1, we're dealing with the 4, but the statistical hypotheses are going to look very much the same. Remember in the previous video for statistical notation we had x equals mu. That's not going to be the case here because now we're dealing with a sample and we're dealing with the mean for the sample. So it will be x bar equals mu. What do those letters refer to? X bar. Well, what that means is that's the average length of the wings of the flies in the terrarium. That's my sample. Then, of course, the notation indicates equal to, so the average length of the wings of the flies in the terrarium are statistically equal to, what does mu mean? Mu was the average length of the wings of the flies in the rest of the house. That's what my population was. So again, if you know what that variable indicates, all you have to do is say it in English, and the hypothesis writes itself. For the experimental hypothesis, it's the same thing, but now we're saying they are not equal to each other. So, now I'm giving you the actual data. These are the 4 flies that I actually captured, and this is the wing lengths for each of those individual 4 flies. You should be able to calculate the average. I encourage you to pause the video at this point and see if you can calculate that average. As we move forward, I'm going to give you all of these values. Here are our formulas that we deconstructed. You have everything that you need because some of the values came from before and we'd already filled in the toolbox, but now you have the actual sample of the flies from the terrarium. So you have the values. You should be able to fill out your toolbox. Once you've filled out the toolbox, you should be able to calculate that z-score, and because that standard unit normal distribution, the z-distribution, doesn't change, you already know that the critical values for that distribution is plus and minus 1.96. Pause the video at this point, try to calculate this through, and make your decision on your z-statistic. If you've computed everything correctly, then what you have in this instance is you're going to have an x bar of 18.5 divided by 4. That ends up being, sigma x is 18.5 divided by 4. Once I actually do that division, we will see that I've got that mean, the sample mean of 4.625. When I plug 4.625 minus 4.5, remember that's my population mean, into my formula, I do have to work up from the standard deviation. I have to convert the 0.2 divided by the square root of little n. What's little n? That's going to be the number of observations in my sample. I had 4. The square root of 4 is 2. So I have 0.2 divided by 2 gives me 0.1. So now I have all the values that I need for my z-score, my z-formula for a group. When I compute that out, that gives me a z value of 1.25. When I then go to my distribution, I note that 1.25 falls in the fail to reject region. What does that mean? That means that I accept the null hypothesis. What does my null hypothesis say again? It says that that group of flies in my terrarium, even though they were larger, statistically were within that range of expected by chance. So this does not support the hypothesis that the terrarium actually encourages or causes the flies to grow larger. So this reiterates what I said earlier. If we find one fly by chance, that's surprising and leads us to wonder or hypothesize about a certain set of conditions. For us, that conditions was the terrarium. So now we want to do an actual research design where we take that environment that we suspect, we introduce a sample because samples are going to be more reliable than one observation. We tend to be more comfortable with that. Once we actually raised the sample and we measured the wings, we found that no, they were not larger than expected by chance. So that one observation was just by chance, quite literally, because the environment does not seem to contribute to a statistically significant difference in the growth of these flies. So we have moved from a situation where we have a special case of a population and we had one observation, but now we compared a sample to that population. But the next video, we will be moving to a t-test for a group. If I'm still using the book, Statistics for Those Who Hate Statistics, when you're watching this video, that textbook does not have the one group t-test. So this will be the only place in the lab manual that I provide and the videos where you will be able to get the t-test for one group, and that's where we will be moving forward to the second instance of a special case for a population that's slightly different from this case. So again, I hope you've enjoyed the videos so far. I hope that they're helping you in your journey through statistics. In the next video, we will again try to link what you're learning that's new to what you hopefully already know at this point.